So the speed of light is always the same in inertial reference frames. It's always c. And we have seen that the time measured by observers, where there's a relative velocity between the observers, is different. And in the previous problem, we saw that not only is the time different, but they would measure distances to be different also. So in problem 30, we had a spaceship going from Earth to the center of the Milky Way galaxy, and the distance as measured by observers on Earth was 50,000 light years. And I'm going to use speed is equal to distance over time to write an equation which is similar to my time dilation equation, but I want to change both of these times to lengths instead. But just like here, we said delta T naught is the proper time, which is measured in a reference frame in which the two events occur at the same place. Because we're going to have two different lengths, we have to identify one of those lengths as being the proper length. Now, you can get an idea of what we would need to do here, because in problem 30, part D, we said that the odometer reading would be 39.9999872 light years. However, although we didn't calculate it, in part B, the spaceship was traveling at 0.9 c, and if the spaceship was traveling at 0.9 c, the odometer reading would be different. It would not be 39.9999872 light years. You would have to replace the 40, no, you'd have to replace, well, the speed and the time to get the distance traveled as measured in the spaceship. So you could see the problem with using the length as measured by someone in the spaceship would be that length depends on their speed. So if you change your speed as you're traveling, the length is going to change also, which gets kind of messy. So the proper length is going to be the length as measured by someone on the Earth, because for someone on the Earth, that distance is always going to be 55,000 light years. So the proper length which we're going to call L naught, is measured in the frame in which the object, which you're measuring the length of, is at rest. But something you have to be careful of is that the frame in which the proper length is measured depends on what you're measuring the proper length of. So suppose you have two different spaceships here. So we have spaceship A and we have spaceship B. And both spaceships are moving. So we have velocity of A and we have velocity of B. If you want to know the proper length of spaceship A, you have to measure in the reference frame of spaceship A. But if you want to know the proper length of spaceship B, that length has to be measured in the reference frame of spaceship B. So in reference frame A, spaceship A is at rest. In reference frame B, spaceship B is at rest. Which also means, suppose both of these spaceships start off at rest, and when they're at rest, they have the same length. Then the spaceships start moving, and sometime later they're passing each other. If you're in spaceship A looking at spaceship B, you are going to say spaceship B is smaller than your own spaceship. However, someone in spaceship B would look at spaceship A and say that spaceship A is smaller. So although the two spaceships had the same length when they were at rest, if they're moving relative to each other, it's always going to look like the spaceship which is moving is smaller. Even if they're both moving, it just depends on what reference frame you're in. Okay, so the proper length has to be measured in the reference frame in which the object is at rest. So we have our proper length here. However, think back to problem 30, whose reference frame was the proper time measured in? The proper time is measured in a reference frame in which the two different events happen in the same place, which was the reference frame of the person who is traveling. So the proper time is measured in one reference frame in this problem, but the proper length is measured in the other reference frame. Okay, so we're going to say in problem 30, looking in the Earth reference frame, we have the speed v, and that's equal to the distance, which is 50,000 light years. That's the proper distance, divided by the time, which is not the proper time because the two events do not occur at the same place. Okay, now in the spaceship's reference frame, the relative velocity is still the same, but now you would say it's the Milky Way galaxy and the Earth which are moving, and your spaceship is at rest. And this is not the proper length because this, if there was a road going from the Earth to the center of the Milky Way, that road would actually be moving. So it's not at rest in the spaceship's reference frame. So it's not the proper length, but divided by the proper time, delta t naught. Then we use our equation for time dilation, and we have delta t is equal to gamma times delta t naught. Gamma times delta t naught. And then the relative velocity is the same for both. So we can put these together and say v is equal to L naught divided by gamma times delta t naught, which is equal to L divided by delta t naught. And then use this. And since you have a delta t naught in the denominator on both sides, you could cancel that out and you get L naught divided by gamma is equal to L. And so this is what we have for length contraction, and they talk about this in the beginning of the book. After time dilation, we have length contraction. So they derive it there, and here we have our formula for length contraction. So we have L is equal to L naught divided by gamma. So suppose it would look better if I wrote it that way. For length contraction, I have L is equal to L naught over gamma. Remember that the smallest value that you can have for gamma is 1, and the largest value is infinity. So if you take the rest length and divide it by the correction factor, you get something smaller. So length contraction says that moving objects shrink. However, what we didn't say, but if we go back to our example here, hopefully you can see, the spaceship is going this way, so in this direction, and you're measuring the length in this direction. So moving objects shrink in the direction that the object is traveling in. So they shrink or are shortened in the direction of motion. Well, how do we know that they're not also shortened in other directions also? So we're going to do a Gedanken experiment for this. So this is length contraction, and now just to check to make sure that we're good in other directions. So if this is the x direction, we would want to check that things don't shrink in the y and z direction, or maybe they do shrink in the y direction and the z direction. How can we figure this out? So we're going to do another Gedanken experiment, again with a train. So we have this train going down the track, and we want to figure out if the height of the train changes. And I guess if the height does change, we could assume the width changes also, and if the height doesn't change, we'll assume the width does not change. So the train is going to be shortened in this direction. Now, alongside of the train, there is a fence. And you're going to ride the train, and you have a bucket of red paint, and you have a bucket of blue paint. and you're going to paint a line on the fence as the train travels by. Now, if the train does become shorter in height as it moves, the wheels of the train, I'm assuming the wheels of the train would still have to touch the ground. So if the train does become shorter in height, it would look like this, but still be on the ground. Okay, so before you begin, you are going to paint a line on the fence. And let's say you paint this line 1 meter above the tracks. Okay, and you're going to paint your red line 1 meter above the tracks. Now, if the train does become shorter in height when it's moving, and you go to paint a line 1 meter above the fence, but now you are measuring in the train's reference frame. Let's do this the other way around. If you are in the train, you wouldn't see the train becoming shorter in height because to you it's the fence which is moving, so the fence would become shorter. So if you are on the train, you would say that the fence is shorter. You would measure a meter with a meter stick in your reference frame, put the line on the shorter fence, and the blue line that you're going to paint when you're riding the train and the fence is shorter is going to appear above the red line. Okay, so the fence is now shorter, but you are not. So you paint the blue line above the red line. However, for someone on the ground, it's the train that is shorter. So someone on the ground, I guess they would say, like, how could you reach that high on a shorter train? Maybe they would say the blue line is below the red line, because if you're measuring with your meter stick on the train, they would look at that meter stick and say, no, it's too short, and your train is too short, so the blue line should be less than a meter above the ground, so they would say it's going to be beneath the red line. Okay, so this would be for observers on the train, this would be for observers on the ground, and they're going to disagree on where that blue line is. Okay, but then the train stops, and you get off of the train, and you go to see where your blue line is. Well, the thing is, at the end of the day, the blue line can't be both above the red line and beneath the red line. And so the only way to resolve this is to have the blue line right on top of the red line. So the train does not shrink in height, the fence does not shrink in height, and the moving objects shrink only in the direction of motion, because that's the only way to resolve the conflict that we have here. Okay, so moving objects are shortened in the direction of motion, and people are going to disagree on which object is shorter based on the reference frame that they are in. And you might think, if there's a conflict here, with the red line being either below the blue line or above the blue line, there should also be a conflict in the direction of motion. And it's true, there is. So you are going to end up in trouble in the direction of motion. However, that is resolved by the relativity of simultaneity. So if there's two things in length, it doesn't seem that it could work out, right? Because if you are in spaceship A and you look at spaceship B, when they're lined up together. So let's say we need these two spaceships to pass. We know that they are the same length when they are at rest. So we would say, well, shouldn't it be just like with our red line and our blue line here? They'd have to be on top of each other, so the tips and the tails of the spaceships would have to be lined up when they pass. Because if they're not lined up, we have a conflict, right? What are we going to do about this conflict? So even though I'm saying one of these spaceships would have to be shorter, it seems like that can't be the case, because how can they both be shorter? Well, if this is one event, when the end of this spaceship lines up with the front of this spaceship, then it is not true that front of this spaceship is lined up with this spaceship at the same time. So for observer A, it would look like this. When this point and this point are lined up, observer A says, my spaceship is the right length, but observer B's spaceship is not the right length, so these two events do not happen at the same time. For observer B, it would be the opposite, and observer B would say when these 2 points are lined up, that's one event, but observer B's spaceship is now the right length if you're in the reference frame of observer A, and observer A's spaceship is shorter, so these 2 points are not lined up. So it is not true that observer A would observe this. It is not true that observer B would observe this. However, let's jump down here. If the magnitude of velocity A is equal to the magnitude of velocity B, then gamma would be the same for both A and B relative to the Earth, so they'd both be shortened by the same amount relative to the Earth. So observer on Earth would see both ships being shorter, but still lining up at the same time. Okay, so now we have our formula for length contraction, and we can use this formula now in some example problems.